Okay, it's time to start some of the actual content of this online review course. And the first thing we're going to do is actually take a look at a little bit of review of some kinematics work that you did in Physics 2204, because this is things that you need to know in order to be able to solve projectile motion problems, which we're going to take a look at in our next class. So what we're going to take a look at today are the kinematics formulas first of all. And all of the kinematics formulas that you need are given on the physics data sheet that is part of your public exam paper. Okay, that will be there in the exam. You can tear it out, use it as you like, but pretty much all the formulas you need will be there. So here are the kinematics ones that you will need to use. Now some of these are a little more common than others. All right. The acceleration formula, which is the first one here on the list, that one is used fairly often. The V2 equals V1 plus AT. Now sometimes that's written as acceleration equals V2 minus V1 over A. Okay, there's lots of different ways to write these equations, and we'll be doing that in just a little bit. The second one there is also fairly common. V2 squared equals V1 squared plus 2AD. That's one way to write it. Another way to write it is 2AD equals V2 squared minus V1 squared, etc., etc. You can rearrange it any way you like. That's the second one right here. And the other one that's fairly commonly used is this one. D equals V1t plus a half of AT squared. D, of course, is the distance or displacement. V1 is the initial velocity. V2 is the final velocity. A is the acceleration, and t is the time that passes while the object is accelerating. Now, all five of those formulas that you see there on your screen, they are all for accelerated motion, uniformly accelerated motion. Now, sometimes there's another equation that you may have to use, which essentially comes from this one here that we're pointing at right now. Okay, I'll just draw a box around it. In this one here, sometimes if the acceleration is 0, in other words, the object is moving at a constant velocity, then the acceleration is 0, and the last part of that equation would disappear then. The half AT squared would be gone, and D equals V times T. That's the uniform motion equation. And we're going to use that one now in this class in a few minutes. You're also going to use that one a little bit when you do projectile motion problems as well, and you'll see that when we get to that later in the week. Anyhow, those are the kinematics formulas. Like I said, all five of those are on your formula sheet, or your data sheet as it's called. And that is exactly the form that they have on that data sheet. In fact, I just took those and copied them directly off your formula sheet. So that's exactly as they appear there, in that order. So let's take a look at some examples where these formulas will be applied. Okay, and remember now, this is just a review of work that you did in Physics 2204. You're probably not going to be asked to do problems like this in 3204, but it's relevant because it leads into the projectile motion stuff. Because projectile motion, remember, means that you're moving in two dimensions, right? You're moving in the y direction, which is vertically, but you're also moving in the x direction horizontally. Now, in all the problems we're going to do here today, we're just going to concentrate on one direction or the other. We're going to concentrate on either the x or the y. And we're going to start off with just x. Okay? So here's the first example. So we've got an airplane that's taxiing down the runway, getting ready to take off, and it starts from rest. Okay, and as you read these problems, it's always a good idea, and I always recommend to my students to do this, write down the given information. Now, even though you're not going to lose any marks if you don't do it on the public exam, okay, it's always a good idea because it helps you choose the proper equation to use. Okay, and that helps in the long run. So starting from rest. So what that tells you is that this plane has an initial velocity of 0 meters per second. V1 equals 0. Okay, it takes off at 175 kilometers per hour. Well, 175 kilometers per hour then is V2. There's only one problem with that number. that is given in kilometers per hour. Normally, when we're doing these calculations, especially when the time is given in seconds, we usually like to have our velocities in meters per second and not kilometers per hour. So the best way to do that is to convert the kilometers per hour into meters per second by dividing by 3.6. Now the reason that works is because in 1 kilometer there are 1,000 meters. Okay, in a kilometer there are 1,000 meters. Let me just write that down. Let me show you where that comes from, that little conversion factor. Okay, so 1 kilometer in 1 hour. Okay, how that works is that means that's the same thing as 1,000 meters in 3,600 seconds. Because that's what 1 hour is, right? 60 minutes in an hour and 60 seconds in a minute. So 60 times 60 gives you 3,600 seconds. That's the same thing as 1 over 3.6 if I basically simplified it down, reduced it down, meters per second. So 1 kilometer per hour is 1 over 3.6 meters per second. That's why I divide by 3.6. Okay, that's where that comes from. So what we do then is the other piece of information that we are given, you'll notice up right here, 32.0 seconds have elapsed. So a passenger is actually timing how long it takes this plane to actually lift off the runway. Okay, so that means that our time is given as 32.0 seconds. So there's 3 variables that we're given. 3 variables that were given. And what is the minimum length of runway required? In other words, how much distance does the plane cover in 32 seconds if it starts from rest and accelerates to 48.6 meters per second? How far does it travel in that time? Well, there's how far. We don't know yet, right? That's the unknown. So D equals a question mark. So what I have here now is 4 variables, V1, V2, T, and D. So what you need to do then is go back to your formula list, and remember you'll have that in front of you because it's part of your public exam paper, and you look for an equation, a formula that has those 4 variables and nothing else. And if you do that for those 4 variables, this is the equation that you'll end up with. Okay, that's one of the equations on the sheet, right? If we go back, there it is. D equals V1 plus V2 over 2 times T. Okay, this guy here, number 5, here he is. That equation has those 4 variables that we're looking for and nothing else. Okay, just those 4 variables. So all we need to do then, we plug in our numbers. So we say 0 plus 48.6 meters per second all over 2 times 32.0 seconds. And when you do that calculation, there's what you get as an answer, 777.6. Okay? 777.6. Now, there's 2 things that you need to think about when you're giving your answers. Okay, and those 2 things are what are the units I should use and how many significant digits am I allowed to have in my answer. Okay, those things are important because on your public exam, and I'm going to mention this several times over the coming classes, on your public exam there are 3 marks somewhere in part 2 that are given for significant digits in units. Now you're not going to know which question that is. So you should give all of your answers with the correct units and the correct significant digits. But it's only going to matter, it's only going to count for points on 3 questions. Okay, 3 questions only, 1 from each unit. So a little tip for you, because I've corrected public exams and I know how these things work. So a little tip for you would be, if you're not sure how to do the answer, okay, write down the formula that you think it should use because that may be worth something. Okay, pick one at random if you're not sure, because like I said, it may be worth half a mark just for figuring out which is the right equation to use. And make sure you write down an answer. Suppose you just pick a number out of the blue. If you're not sure how to do it, write down an answer with the correct number of significant digits and the correct units. And if that is the question that was designated for significant digits and units, we call it science and communication, then you will get that mark, whether your answer is right or not. It doesn't matter. Okay? You'll still get that mark. It may be one of the 4 marks, for example, that question is worth. All right, so keep that in mind. For this particular question right here, if you look up at the numbers we were given, this number here, 175 kilometers per hour, that V2, that has 3 significant digits. The time has 3 significant digits as well. The first velocity, V1, said it started from rest. That's exactly 0. Now, exact numbers have an infinite number of significant digits. And then all you got to remember is the rule is when you're multiplying or dividing numbers, the rule for significant digits is you round your answer off to the least number of significant digits, the least number. And the least number here will be 3. So if I want to round this number off to 3 significant digits, then I would say 778. But that's only part of the answer. The other part of the answer is the units, and for this particular one, because it's a distance that we're looking for, the units are meters. Okay, so now you've got the complete answer. 778 meters is the right answer. It has the right number of significant digits, and it has the right units. Full marks. Okay, so keep that in mind. Significant digits and units are important. They're only going to be graded on 3 questions, but the problem is you're not going to know which 3 questions. So you should always try to give your answers with the proper numbers of significant digits. Let's try another example. Also an object moving horizontally. Another airplane. Okay, already moving this time. This doesn't start from rest. It's already moving at 11.0 kilometers per hour. It enters a runway stretch and requires a distance of 1.22 kilometers to take off. The acceleration of this plane is 1.60 meters per second squared, and it's maintained. In other words, we're going to assume that it's a constant acceleration, a uniform acceleration. In this particular course, that has to be the case, or you can't really solve it. Okay? Determine the time required to take off. So let's do the same steps again. Let's write down the information that we're given. So the first thing we're given is V1. But it's in meters per second, or sorry, it's in kilometers per hour and not meters per second. So we're going to divide by 3.6 to do the conversion, and that will give us 3.06 meters per second. I know that the distance the plane travels while it's taking off is 1.22 kilometers, but again, that's the wrong units. We want to change that. So multiply by 1,000 because there's 1,000 meters in a kilometer. And that will give you 1,220 meters. The other information we're given for this one is the acceleration is 1.60 meters per second squared. And the time required is the question mark. I call it the unknown. So that's the next thing that we need to write down. So we pick an equation, we pick a formula with those 4 variables in it, and we get this equation. D equals V1 times T plus 1/2 of AT squared. That's the formula that works. Now, only thing is, when we plug our numbers in, look what happens. We've got a T right here, and we've got a T squared over here. So that's a little more difficult to solve. So what we're going to have to do with this one is I'm going to rearrange it so that all of my numbers are on the same side and it's equal to 0. So I'm going to rearrange it so it looks like that. Okay, and you should all recognize that form of an equation because you've not only seen it in physics, you've also seen it in mathematics. That is what we call a quadratic equation. Okay, it has a squared term. It has a linear term, in other words, a t with no squared on it, and it has a constant term. That's what we call, that's the standard form for a quadratic equation. So if that's a quadratic equation, then we can use the quadratic formula. And the quadratic formula just happens to be on your formula sheet. Okay, the quadratic formula is on your formula sheet. It is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now you might ask, what do the a, b, and c mean? Well, those are the coefficients in our equation, right? The a is the one in front of the squared term, the b is the one in front of the linear term, and the c is the constant. Okay, so there are the numbers right there. A equals 0.8, b equals 3.06, and c equals negative 1,220. All right, so we take those, we plug them into the quadratic formula. So it looks like that. And instead of saying x equals, I just said t equals, because time is what we're trying to find here. Okay, time is what we're trying to find. So we plug those numbers in. We plug in b, a, and c into the quadratic formula. Like I said, the quadratic formula is on your data sheet. It's on that formula sheet that you're given for the physics exam. So you don't have to worry about memorizing it even. It's already there. So there's your numbers plugged in. Then we just start solving that with our calculator. So the first thing we're going to do is what's underneath the square root sign and take the square root of it. And we get that expression. 62.56 is the square root of 3.06 squared minus so on and so on. All right. Now, the plus or minus means that there are two answers, because quadratic formulas have two solutions for any given time. Or there's two times, sorry, for any given position. Because remember, when you throw an object up in the air, it's at a certain position at two different times. So there's two possible answers, in other words. One is the plus, the other is the minus. So there's what we do. We put a plus sign, we put a minus sign, and we solve. We solve that equation. When you do that, one of the answers you get is 37.2, a positive 37.2. The other answer you get is a negative 41.0. Now, this one is pretty easy to figure out which of those answers is the correct answer, because you know that time, not being a vector quantity, it cannot be negative, right? We can't have a negative time. Time doesn't have direction. The negative indicates direction. So that means that right away we can disregard this answer right here, because that answer is a negative time. Doesn't work. So the correct answer then has to be the other one. So here's our answer right here. We can eliminate the other choice. We know that the time must be 37.2. Now, some people don't like using a quadratic equation. So what we're going to do, I'm going to show you a different way to do it. I'm going to show you a different way to solve that. There is another way avoiding the use of the quadratic formula. Okay, so let's do the exact same problem all over again. An alternate solution. So we still write down our given information just like we would before. Okay, there's all the given information. But if I just plug that into a formula, I'm going to end up with the exact same thing I had before. So what I can do instead is this. I can find V2 first. If I find V2 first using a different equation, I can then use that value of V2 to find the time a different way. So if I'm going to find V2 first, I'd use this equation right here. And that's basically V2 squared equals V1 squared plus 2AD. That's the way it's written actually on the formula sheet. Just like that. So we plug our numbers in. Same numbers we had before, the 3.06 for V1, the 1.60 for acceleration A, and the 1220 for D. Do that, and you get V2 squared equals 3913. Now, because that's V2 squared, we need to know what is the square root of that. But you got to be careful when you take the square root of a number, because every time you take the square root of a number, there are two possible answers. There's a positive square root, and there's a negative square root. Okay, there's a positive and there's a negative. Now, which one is right? Well, you got to use a little bit of reasoning, a little bit of common sense to figure that out. In this particular one, it doesn't give us any directions. The plane is just traveling in the same direction all the time. It doesn't change direction at any point. So we're just going to go with the positive solution. 62.6 is the square root of that number, and we're going to call that a positive 62.6. That's V2. In other words, that's the speed of the plane just before it takes off. Then we can use that value in a different equation, this one, the acceleration formula, v2 equals v1 plus at. Okay, we rearrange it so that it's t equals v2 minus v1 over a. That's the same equation, just written in a different way. Plug those numbers in, and you get an answer of 37.2 seconds, the exact same answer we had before. The exact same answer we had before. By the way, if you put a negative 62.6 here, because remember there are two possible values for v2, we just knew that the right answer was positive, and you plug the negative 62.6 into that equation, you'd actually get the negative 41.0, the other answer that we got using the quadratic formula. So you can get both answers this way too, in other words. Okay? So that's that one. So there's nothing overly complicated about that. That's just some stuff that was done in Physics 2204. Now let's look at some vertical examples. In other words, vertical motion. So this one here, we've got a hot air balloon that's moving upwards at a constant velocity of 3.7 meters per second. And at the instant that it's 6.5 meters above the ground, you toss a ball straight up with an initial speed of 12 meters per second relative to the balloon. So the situation is this. Okay, there's the ground. When you're right here, you throw a ball up in the air. The ball goes up in the air like that and then falls right back down to the ground afterwards. That's the situation. Okay, we want to know how much time passes before the ball ends up back down in the grass. Okay, so how do we do it? Well, we write down our given information first. Our given information is the ball was thrown at 12 meters per second, but it was in a balloon that was already moving at 3.7. So we actually have to add those two speeds together to get the speed of the balloon relative to the ground, or sorry, the speed of the ball relative to the ground. So the speed of the ball is 15.7 meters per second. We know that the distance is negative 6.5. Now the reason it's negative 6.5, you just look right here. The ball starts here, but it ends up down here. It actually ends up lower than where it started. That's why I have to say negative 6.5, because by the time the ball hits the grass, it has fallen 6.5 meters. Now it went up and came down, but the net result is it ends up 6.5 meters lower than where it started. So that's why I have to put that negative sign there. And that negative sign is very important. The acceleration is negative 9.80 this time because it is a free-falling object. Anything you throw up in the air will always have the same acceleration, negative 9.80. And then we say time is the question mark. So now again, I could say d equals v1t plus a half at squared, and I'd have to use the quadratic formula. Or I could find v2 first. Let's do finding v2 first. So we find v2 first. We use this equation again, straight off the formula sheet. Plug in the numbers, the values that were given, making sure the signs are correct, right? We got two negative signs there. And when you do that calculation, you get this. Again, the plus or minus is very important. Now this time, you'll notice the answer is negative. Now, we know the answer is negative because just before that ball lands on the ground, it has to be traveling downwards. That's why it's a negative 19.3 and not a positive. Now again, that negative is very, very important. It needs to be there. And we're going to come across some of those later on when we do projectile motion ones too. So then we just plug that into that formula like this, and we get an answer of 3.6. Now, if you had used a positive 19.3 in that calculation, you would have ended up with a negative time. And you would have known that something went wrong somewhere. So watch for that. If you had put in a positive 19.3, you would have gotten a negative time, and right away you'd know you made a mistake. Or you should know anyway. All right. How far did this ball travel altogether? How far did it travel altogether? Well, we got the v1 is the same, but this time I don't know the distance, so I can't say d equals negative 6.5 anymore. But what I'm going to do is, if I want to know how far it goes, well, I just need to know how far did it go up and then how far did it fall back down again. So in other words, I need to find the maximum height. And if I'm going to find the maximum height, V2 is 0. Okay? At the maximum height, V2 is always 0. So what I'm going to find first is the maximum height. And again, the acceleration is negative 9.80. So we use this formula again. I rearrange it this time for D instead of V2. So I write it that way. Okay. When I plug in my values, I get that. And there's my maximum height. That's how far it goes up from the balloon. So remember now, the situation was, it started, here's the ground, it started here, it went up, 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 and then down, 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 down. So from here to here was 12.6. That means from here back down to here was also 12.6. And at the instant it was thrown, the balloon was already 6.5 meters above the ground. So to get the total distance, all I got to do is add all that together. Okay, and if I add all that together, here's what I get. I get total distance is 12.6 up, then another 12.6 down to get back where it started from, and then another 6.5 to get all the way to the ground. Add all those together and round it off to 2 significant digits, you would get an answer of 32 meters. And that part is done. Okay, so that's not terribly difficult either. And then the third part of this question asks, what is the altitude of the balloon? In other words, how high is the balloon when that ball lands in the grass? Well, all we got to do is use the time that we found in part A, because the time that we found in part A is the time it took that ball to go all the way up and all the way back down to the ground again. So that's how long the balloon would be moving. And the balloon was moving at a constant speed of 3.7. It told us that right back at the beginning of the question. And because this is uniform motion, all I have to do is say D equals V times T. And I know V and T. Multiply those together and you get 13 meters. But remember now, that's 13 meters higher than it was at the beginning. And at the beginning, it was already 6.5 meters high. So we have to add on that 6.5. That gives us 19.5. And when you add numbers, you go with the least number of decimal places, which would be no decimal places. So you would have an answer of 20 meters high. That's how high the balloon is when that ball goes up and comes right back down to the ground again. Okay. One last example before we stop. And it looks like this. Similar type of situation, only this time you're not in a moving object. You're standing at the bottom of a cliff, and you toss a softball up to your friend who's standing on the edge of a cliff. So this time the situation looks like this. Let's just draw a real quick sketch of this again. Okay, so here's the cliff. Okay, you're standing down here at the bottom. Your buddy's standing up here at the top. And you throw a ball up in the air like this, all the way up, 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 and it comes, he catches it on the way down again. He misses it on the way up, he wasn't paying attention. But on the way down, he manages to catch the ball before it falls down to the bottom of the cliff again. Okay, the initial speed of the ball was 25 meters per second. So let's take that information now and write it in. So the initial speed was 25.0, and it's up, so it's positive. Okay. Also, the distance, it ends up 10 meters higher than where it started, so it's positive 10. Okay. We got acceleration equals negative 9.80 because this, again, is a free-falling object. Any object traveling through the air is that acceleration. And we're trying to find the time. So again, we've got two choices. When you've got that kind of information given and you want to find time, you could use the quadratic, or you could find V2 first. Okay, now I've already done it twice using V2 first, but I've only done it once using the quadratic. So let's do the quadratic again. Okay, we use this equation, D equals V1t plus a half AT squared. We plug in our numbers, right, for D, V1, and A. We leave the T and the T squared. And when I rearrange it, I get this. This time I'm bringing everything over to the left-hand side. Doesn't matter. You could leave it on the right-hand side and change all the signs. It doesn't matter. I could have had, for example, 0 equals negative 4.9 plus 25t minus 10. That would have worked too. Just all my signs would be opposite. We're going to use the quadratic formula, and we're going to have a, b, and c equal to those values because they just come straight out of that quadratic equation. We plug them into the quadratic formula. So it looks like that, right? Remember, negative b plus or minus the square root of b squared minus 4ac all over 2a. And again, that equation, that quadratic formula, is on your formula sheet. It's given to you. Okay, so we plug those in. Here's what we get. I do what's underneath the square root sign first, then take the square root, and I get 25 plus or minus 20.7 all over 9.8. Now again, remember there's two ways to do that. One of them is the plus, the other is the minus. 1 plus, 1 minus. Alright, so the plus gives us this answer, positive 4.66, and the minus also gives us a positive answer. So this one is a little bit tricky, isn't it? We've got two positive answers, so we got to figure out which one is the right one. Well, here's the key right here. The key to this question is the ball is caught on the way down. So if it's caught on the way down, if he misses it on the way up, well, on the way up, that was this time, look. This was on the way up. This was on the way down. Okay, because it actually passed your friend at the top of the cliff twice, once on the way up and once on the way down. So on the way up he missed it, so we know that this time is wrong, but he did catch it on the way down, so that means that second time is correct. So you really got to read the question carefully sometimes to figure out what's being asked. Okay, so there's a little bit of practice of kinematics, and we're going to use that kinematics in our next class to solve some projectile motion problems. And the reason I did examples using horizontal motion and vertical motion here is because when we do projectile motion, we have both of them in the same question. But it's not as hard as you might think. Alright, so we'll leave it at that. Study hard, and we'll try some projectile motion questions in the next class.